Hello and welcome. Section 1.1, we'll go through a little bit with definitions and some terminology. So an equation containing derivatives of one or more, I just kind of write as one superscript plus one or more unknown functions or dependent variables with respect to one or more independent variables is a differential equation. If we have one independent variable, it's referred to as an ordinary differential equation. See ODE used a lot for that. Two or more independent variables, it's a partial differential equation, PDE. When we're working with differential equations, one thing of interest that we look at is the order. Find that by just finding the highest derivative in the equation. So for example, fourth derivative minus third derivative plus 2 times second derivative plus 3 times first derivative minus 4 times the function is worth negative 19. That is a fourth order differential equation. The highest derivative we took was a fourth derivative. If we have an equation that is a differential equation and it is set to 0, that's referred to as the general form. So superscript n is referring to the nth derivative. So if we're set to 0, this is the general form. Normal form would be isolating the highest derivative. So this last one is the n minus first derivative. This is the normal form. So both are used, just different ones in different situations, just like in your algebra and calculus days. Now we do have what we refer to as linear differential equations. It's a slightly different shade of meaning on it than just a regular linear equation from your algebra days, though. But the same basic core values in it. So in diff-EQ, we're talking about linear with respect to y. WRT with respect to. That's sort of a common math abbreviation. All right, so some examples and counterexamples on that. 5y double prime plus 7y prime plus x squared y equals 2 is linear. So you might see this x squared and say, okay, that doesn't sound linear. With differential equations, we only mean with respect to y. So here we had a y by itself, first power, and y prime, again, just one of those. We didn't have y prime squared. We didn't have a fourth root of y prime, etc. Y double prime, same idea. We didn't have e to the y double prime or anything like that. Those were just this thing by itself times some function of x. So some nonlinear examples, 7y double prime plus 8e to the y equals 2. The fact that I have an e to the y says that is nonlinear. Same thing if I had 5y y double prime equals 19. The fact that I'm multiplying two things that are written with respect to x's in one term makes this nonlinear. A couple of the more valuable linear forms. I have a sub 1 of x, so some first function of x times y prime plus a naught of x times y equals g of x. This is a first order linear. So first order, remember, order is just the highest derivative. First derivative was the highest we took. Similarly, we have a second order, sort of a cousin to our quadratic equations back in your algebra days. So a sub 2 of x times y double prime plus a sub 1 of x times y prime plus a naught of x times y equals g of x is a second order linear. All right, so another definition here. A function phi on open interval I that has at least n continuous derivatives on I, which when substituted into the ordinary differential equation reduces to an identity E is a solution to the equation on I. And we'll kind of see some examples of what that means in plain English. So basically, in your algebra days, you learn to plug in a hypothetical x value into a function and see if it works. See if you got 10 equals 10, 2 equals 2, 0 equals 0, 0 equals 0, etc. Same idea here, except you would plug in a function rather than a constant to see if we have a true statement at the end. So for example, we can verify y equals e to the x cosine of 4x is a solution to the ordinary differential equation y double prime minus 2y prime plus 17y equals 0 on the real number line, negative infinity, infinity. All right, so it looks like we'll need a second derivative, which means also we'll need a first derivative. So let's go ahead and get those. So y prime, this is just a simple product rule one. Derivative of the first factor, keep the second factor, plus now keep the first factor, differentiate the second factor. Just to make that easier to work with, since we're going to be doing another derivative in a minute, I'll go ahead and factor that guy. So e to the x by cosine of 4x minus 4 sine of 4x. So then our second derivative, y double prime, product rule again. Derivative of the first, keep the second. Plus, now do the keeping of the first, differentiating of the second. So derivative of cosine of 4x, negative 4 sine of 4x. And derivative of negative 4 sine of 4x would be negative 16 cosine of 4x. So we can put some of those together, and of course, once again, factor e to the x. So y double prime, I'll factor that e to the x. So I have, let's see, cosine of 4x and minus 16 cosine of 4x would be minus 15 cosine of 4x. And minus 4 sine of 4x minus another 4 sine of 4x would be minus 8 sine of 4x. Okay, so we have our original equation. We have our first derivative. I'll go with the simpler version of our first derivative and our second derivative. We're going to plug those in to this is our differential equation. So the right-hand side is pretty easy, so we basically need the left-hand side. So we use LHS as a common abbreviation for left-hand side. So y double prime, that's this guy. So e to the x by negative 15 cosine of 4x minus 8 sine of 4x. So there's our y double prime. Then we have minus 2 times y prime, e to the x, cosine of 4x, minus 4 sine of 4x. Close that parenthesis, that parenthesis, that parenthesis. And finally then plus 17y. I'm just going to use an arrow since I am out of real estate there. So plus 17 times our original y, e to the x cosine of 4x. So each one of those had an e to the x on there. Then I have minus 15 cosine of 4x, minus 2 cosine of 4x, so there's minus 17 cosine of 4x and plus 17 cosine of 4x. That is a 0. Negative 8 sine of 4x plus 8 sine of 4x. So remember, we're distributing that negative 2. Right-hand side was already a 0. 0 equals 0. Our solution does check out. So this is a solution on negative infinity, infinity. The x is differentiable everywhere, so is cosine. Later sections will also get into, okay, well, instead of just rabbit out of the hat, they told us this is our solution. How do we find a solution? So next we'll verify y is 1 over x is a solution to xy prime is equal to opposite of y. Well, for starters, we'll call this y x to the negative first, so then y prime, negative 1, x to the negative second. So we have our y, we have our y prime. This time we don't have any y double primes. I don't need a second derivative. So the left-hand side, we have x, y prime. So that is x times negative 1, x to the negative second. So that's x times negative 1 over x squared. So that's negative 1 over x. Right-hand side, opposite of y. So that's opposite of x to the negative first. So that's negative 1 over x. Left-hand side equals right-hand side. So this does work. Negative 1 over x equals negative 1 over x. But this time I can't say this is true everywhere. Clearly, looking at our denominators, x equals 0 is going to throw us into undefined territory. It will work everywhere else. So I have to pick an interval. So this is true on either 0 infinity exclusive on both, or on negative infinity 0 not negative infinity infinity. We usually wouldn't write this last part. We would just sort of pick an interval, pick the largest interval where we do have a true statement. In this case, they're both the same, so either interval would just be fine. I couldn't just say this is true everywhere. I can't say that it is on negative infinity infinity. Next, we look at a little bit about implicit solutions versus explicit solutions that you've seen starting in your college algebra days. So an implicit solution would be something maybe x squared over 4 plus y squared over 25 equals 1. So an ellipse. Since we don't have a y by itself, this is an implicit solution versus an explicit solution. We would have the y by itself. So this one is an implicit solution. I didn't give you what the diff EQ was to the y prime equals negative 25x over 4y. If we had the y by itself, that would be an explicit solution. This one you can verify. Simply differentiate both sides. So derivative with respect to x of the left-hand side is derivative with respect to x of the right-hand side. So x squared over 4, derivative then would be x over 2, or 1/2 x, whichever you want to think of it as, plus 2/25 y prime equals 0, and get that y prime by itself then. So 2/25 y prime is opposite of x over 2. So then we multiply by 25 over the quantity 2y on both sides. So y prime is negative 25x over, there's our 4y that we were expecting to see. If we wanted an explicit solution, as I mentioned, we would just get the y by itself. So y squared over 25 is 1 minus x squared over 4. So then y over 5 is plus or minus square root of 1 minus x squared over 4. So y is plus or minus 5 root 1 minus x squared over 4. And these are solutions negative 2 to 2. Anything outside of that, and we're doing square root of a negative, we're getting kicked out of the real number system then. All right, so solutions in differential equations, think back to your calculus days, they can be either a family of solutions or a particular solution. It depends on if they give us some initial conditions or not. So for example, if we consider y equals ce to the x, that is a family of solutions to y prime minus y is 0. And you can verify that pretty easily. Y prime here is still ce to the x. Ce to the x minus ce to the x is 0. 0 equals 0. But if they give us some initial conditions, they can ask us for a particular solution. So for example, they might tell us y of 1 is 3. Well, then we just plug in what we know. So 3 is worth c e to the first. So c is 3 over e. So then the particular solution will be y equals 3 over e times e to the x. That one would be on negative infinity, infinity. That one would work everywhere. So sometimes a family of solutions, sometimes a particular solution if they give us some more information. We will also occasionally run across systems of differential equations, and it's just what it sounds like. So we have x is something like e to the t plus 8 cosine t. Y is worth e to the t minus 8 sine of t. Those are solutions to dx dt equals y, dy dt x minus 16 cosine t. So to verify that, my apologies, we're starting with dx dt. So dx dt, differentiate this with respect to variable t. Derivative of e to the t is still e to the t. Derivative of cosine is negative sine, so minus 8 sine of t. And sure enough, that is equal to our y. As promised, dx dt did end up as y. If we find dy dt, Derivative of e to the t is still e to the t. Derivative of sine is cosine. Excuse me. So I want to know, is e to the t minus 8 cosine t the same as what we're claiming it's equal to x minus 16 cosine t? Well, x, as we know, is e to the t plus 8 cosine t. So left side I have e to the t minus 8 cosine t. And I want to know, is this equal to x gets replaced with e to the t plus 8 cosine of t. And then I still have this minus 16 cosine of t. Well, I have plus 8 cosine t minus 16 cosine t. Well, that does indeed simplify to what we needed. That does give us an identity, so that does work out. Okay, so the problems I would recommend looking at, this was in section 1.1. I would try at 1 to 37 the odds. If you have trouble, make sure you get in touch with me, and I will see you for the next video. Thank you, and stay safe out there.